Well, welcome back. We're into lesson 3, similar triangles, and specifically application problems. And this is where it does sometimes get a little bit more challenging, but sometimes you think, how do you actually find the height of something like a hill or the distance of a river if you couldn't actually measure it? It's an immeasurable thing. Could you find out the height of a flagpole that's out in front of your school? And the answer is yes, you could. And the learning goal here is to solve problems using or involving similar triangles in realistic situations. Shadows, reflections, scale models, surveying. A sample problem using a meter stick to determine the height of a tree by means of the similar triangles formed by the tree, the meter stick, and their shadows. And there's multiple ways of doing this. In fact, if you were to look at surveyors when they're outside, they got these instruments. Well, the instruments are essentially using similar triangles. And actually, primary trig ratios, which is a lesson which you're going to learn in an upcoming lesson after this one, it's all derived using similar triangles. It's just, but it converts into functions in your calculator. Here's your first question, which is based on the diagram, determine the scale factor and the value of x and y. At this point, I'd encourage you to pause the video and see if you can do this on your own, and that way you will struggle a little bit, but that is where the learning happens. In this case, the first or the most important part is the starting point, and what I'm going to do is I'm going to deconstruct these into two separate triangles. A smaller triangle, which is this one here, and the larger triangle, which is this one on the outside. And so we get this new diagram which is updated. And the smaller triangle you don't have to do any calculations for, but when it comes to finding out the larger one, the 15 comes from the 12 plus the 3. That's where the 15 comes from. This 10 plus x comes from this side length here, which is 10 plus x. The bottom remains 20, and we've essentially just transferred those numbers down for the smaller one, down to the smaller triangle. I like having this big block of stuff. Maybe what I can do is I can recapture this slide. Let's go back to my video. Recapture here. Alright, so here's what's going to happen. I'm going to try and match up the side lengths. So let's just say I want to solve for x. Well, I'm going to start with 1, and I know it corresponds to this 10. So here's what I'm going to write. I start with what I want to solve for. 10 plus x over, I bounce over to this one, over 10. I come back to this triangle here, and I start with two sides which I can correspond and know both values for. And in this case, I know the 15 and the 12. So I started on the big triangle. I'm going to start on the big triangle again. Ooh, why did that come over here? Let's go put that back onto the dock. This is equal to 15, and now it's linked to this 12 over 12, and now it becomes a simple case of solving an algebraic expression. Cross multiplication, the 12 comes up to this side, it's 12 times 10 plus x, and I'm going to simultaneously do this with the 10. The 10 comes up and multiplies the 15. And so this would, distributive properties means we multiply through the brackets by the 12. So this would become 120 plus 12x is equal to 150. So now a two-step equation, 12x is equal to 150 minus 120. 12x is equal to 30. Divide by 12, divide by 12, and this is not going to be a nice answer. It will be x is equal to 2.5, I believe, 2.5. Does that make sense when we look at this diagram? Yeah, I thought it was going to look a little small, but at the same time as I look at this, this is a 10 plus a number. Alright, now we're going to solve for y. So I always start with the variable I want to solve for. I'm starting with the y. That corresponds to the 20. So I'm going to start with y over 20 is equal to, I'm going to start back onto the small triangle, so it always goes small, big. I'm going to go small, big again, 12 over 15. So I now have a fraction. I always start with the variable that I want to solve with first, because that way it's on the top, and I don't have to do an extra step when solving the equation. Y is equal to 12 times 20 divided by 15. That's going to be equal to, let's see here, I can divide the 15 into 12, that's by 3, that's 4. This is going to be 5. 4 times 20, oh wait, I can divide 20 by 5, that's 1. This is 4. So y is going to be equal to 16. So we found the value of x and y. We did not find the scale factor yet. To find the scale factor, we can do 12. We just take these numbers here, one side over the other. So n would be equal to 12 over 15. Using my trusty calculator, that scalar factor is, by 15, 0.8. So this is equal to 0.8 is the scalar factor. Alright, let's come back to our next question. Skip past that. How tall is the building if Maggie is 4 feet 9 inches? And in this case, we've got this situation where we can assume that these are similar triangles, because the top of her head creates, when looking at a mirror, will then end up lining up at the top of the building. This angle will be equal to this angle due to the way physics works with mirrors and visually. What else? So we got two angles which are the same. On the angle that'll be made with the horizontal, we'll assume that she's standing upright. So there are two angles which are the same. Let's see here. What do we need to start with? Well, this is 4 feet 9 inches. We need to convert that into feet only. And there are 12 inches in a foot. So that's going to be 4 plus 9 over 12, which gives us 4.75, which means that her height is 4.75. Now, where did these numbers come from? Maybe what I should do is I should create a new diagram here so that we can do a little bit more with it. So what happens is, here's one triangle. That's 4.75. This is 5. And then if we were to take this other triangle and flip it around, it's similar to this one here. This is h, this is 100. And when we solve for h, we use corresponding sides. So this will be h over 4.75 is equal to, we went big to small, now we got to go big to small again, is equal to 100 over 5. So h is going to be equal to, well, 100 divided by 5 is 20. And that 4.75 comes up times 4.75, just doing two steps in one. Get out my trusty calculator. 20 times 4.75 is 95. So it tells me that the building is going to be 95 feet tall, equals 95. Therefore, the building is 95 feet tall. A final statement. Horrible writing, but it works. Alright. That's what we got here too. Yay! Well, what if she was 5 feet 5 inches? Well, I encourage you to pause the video and try and do that on your own. Essentially what happens is we just change her height. To go through that, the process would be the same, except instead of being 5 feet 9 inches, it would convert into 5.24 feet. Same calculation. Again, it's a good way to double check. Based on the diagram, determine the height of the flagpole. This question confuses a lot of students, and it's primarily because they try and use the 15 alone. We have to think of these in two different triangles. This big triangle, and then there's this small triangle. And I strongly recommend that you make 2 separate diagrams, because if you don't, you're going to make a mistake. 1.5 meters here, 1 meter here. Where are people going to make the mistake? They're going to make it on the big one, because this is not 15. It's 15 plus 1.5, which is going to be 16.5. And the height of the flagpole, and gotta make sure I get a better diagram, is going to be h. We label it with what we want to find. So we start with a variable that we want to solve for, h over, it corresponds to this 1 here. These are corresponding sides. And we went big to small, so we go equal to big to small again. This is going to be 16.5 over 1.5. And there's not, h divided by 1 is just h, so we just need to do 16.5 divided by 1.5. 0.5 divided by 1.5 is equal to 11. So what this tells us is that the height of the flagpole is 11 meters. The pole is 11 meters tall. Hey, look at that. My nice solution here. Also had it broken up into 2 different diagrams. Again, strongly recommend that whenever you have a triangle inside of a triangle, that you make 2 separate ones. And now that also explains where the 16.5 comes from. This one's a little bit less messy than my writing. Last question. Using the length of the shadows, determine the height of the goalpost in green. I encourage you to pause the video and try and do this on your own. This is going to be x. Do I even really need to write this? Well, the height represents the height of the goalpost. The triangles are similar based on the angle of the sunlight and the vertical being 90 degrees to the ground. So whenever a sun shines, it's going to create the same angle as long as these 2 sides are both upright and perfectly vertical. So the height of the goalpost is 12.5. Well, that's not very helpful. Let's show a little bit more math to that. Now what's going on here? This is h, and in this case, we're going to start with h. H over, so we went, this corresponds to this side. H over 1 is equal to, went big to small, so we go big to small, 2.5 over 0.2. The battery's dying on this 10.2. And so h, well, 0.2 is 1 over 5, so 5 times 2.5 is going to be 12.5. Therefore, the goalpost is 12.5 meters tall. That's it for this class. Similar triangles can be tricky. Practice will make perfect. There's several questions for you to do on page 348, as well as there's some questions on the right here for those who need the additional practice. For the most part, you could have done question number 1 in the last lesson, but the ones after it are application problems, and there are answers at the bottom. Thanks for watching, and good luck on your studies.